And welcome. In this video, I am going to prove that given the finite group G of automorphisms from E on to E with fixed field F, there is an associated Galois extension E over F with Galois group is equal to G. So let's say that sigma 1, sigma 2 up to sigma n being the elements of the G, and we consider an element of E alpha, and beta 1 up to beta n are the beta m are the images of the alpha through this all the automorphisms. So let's say sigma be an any automorphism of G, any automorphism from G. Okay, so these are beta 1 up to beta m are the distinct elements among these images. Okay, so these images are n of them because, and there may be repetition, so therefore the distinct elements will be beta 1 beta up to beta m, where m is less than equal to n. So note that since these are the distinct sigma 1 to sigma n are the distinct automorphisms, so sigma, and this sigma is one of among them, so sigma of beta 1 to sigma of beta m are distinct. Okay, so these are the distinct automorphisms, and also we can note that the composition sigma beta 1 so sigma 1 to sigma n, these are also distinct because this sigma 1 up to sigma n are the distinct. So we first take the images under this sigma 1 up to sigma n, and then we take the image under sigma, which is any automorphism. So there are n among n of them, and they all are distinct. So this G is a group which contains n elements. So all the elements of G will coincide with this element. So they are all distinct and they coincide with elements of G. So this set is equal to all the sigma 1 up to sigma n. So we can say that sigma I is equal to sigma j for some I j. Okay. So if I apply alpha to this element, sigma 1 of alpha to sigma 1 of alpha, sigma n of alpha, then they will coincide with these elements. And this sigma 1 of alpha is what? It is beta 1, right? So since they are the same elements, they are distinct, so we can say that sigma I of alpha is equal to sigma j of alpha is equal to sigma of alpha is some beta j, so beta k, some beta k, and sigma j of alpha will be equal to some beta, say m, for some k, m, I and j. So what is happening that these are the beta 1 up to beta m are the distinct elements among the images of alpha under these automorphisms, and under the any given automorphism from the group, they are it is just altering them and mapping onto the same set. So it is just a permutation. So sigma sigma is just permitting the images of the alpha for any element of the G. Okay. So now if I consider f of x, let f of x be an polynomial in E of x. So f of x is in E of x. So it is polynomial or E of x. And we know that alpha is element of E. Okay, so I will consider f of x is equal to product of x minus bi. They are distinct among them. So if I take the automorphism of f of x, then what will happen is x minus beta I, and this product of the sigma of this x bi which is equal to sigma of x minus sigma of bi's, because x will be invariant under them. So sigma of bi's will be equal to some bj, right? So sigma of f of x will be this product, and since this sigma is any automorphism and it alters just bi, so it will be equal to j running from 1 to m x bj. So, and this is equal to f of x because it is just changing the indexes. Okay, so what we got is that sigma of f of x is equal to f of x. So though this automorphism sigma does not only change the images under any element of E, it also changes the polynomial. It does also keep the any polynomial also it keeps invariant. So any polynomial over E of x is invariant under any automorphism. So what does that mean? That f of x is belongs to f of x. F is the base field. So, and we know that this all bj's are there in E. So this f of x is a polynomial over f, and it has all its roots inside E. So what is that? What does that mean? And they are distinct. All the roots or this b i's are distinct. So what does that mean? That f of x is separable over f. So f of x is separable polynomial over f. And now I want to prove that this extension E or f is separable extension. So I need to just need that f of x is irreducible. So suppose if it is not irreducible, then there exists some polynomial g of x is minimal polynomial of alpha, and we have g of x is equal to so g of alpha is sigma of alpha is equal to what? So I will take the images of alpha under all the automorphism. So it is equal to sigma of g of alpha, but g of alpha is 0 because g is minimal polynomial, which is equal to 0. So what does that mean? And this alpha is images of sigma is, and of the image of alpha under sigma is beta is. So g of beta is equal to 0 for all I, and they are distinct. So what does that mean? That beta 1 up to beta m are the distinct roots of g of x. So they are also distinct roots of f of x. So since it is minimal polynomial, degree of g of x will be greater than equal to degree of f of x. What does that mean? That f of x divides g of x. since so f of x divides g of x, and what we can say, the so f of x is a polynomial. It is any polynomial, and we have considered g of x is a minimal polynomial. So since g of x is minimal, it is irreducible, and since g of x is minimal, it is irreducible. So f of x will be equal to g of x. So that proves that for any element alpha of e, there is a irreducible polynomial which splits linearly over f. So e of f is an separable extension. So we have shown that in e or f is a separable extension. So now I will show that we will show that e over f is a finite extension. Then we will show that it is normal, and then it will be Galois extension. Okay. So since it is finite, it will be algebraic. So we will have algebraic, finite, separable, and normal. Therefore, it is Galois. So for showing it is finite extension, let's say let n over f be an finite extension where n contain inside e. So that is n is what? N is contained inside e. Then n over f is a separable extension. And since it is separable, it is finite separable extension. So therefore, we know that n can be written as f of beta for some beta belongs to n. Okay, so now that its index of n over f will be what? Of beta. So what does that mean? Beta is algebraic over f, and for a number of roots of the irreducible polynomial of beta over f will be n. Will be less than equal to n, because beta is our distinct element. So so beta is just any element of n. So for any polynomial, if it has distinct roots, then there will be n roots among them. So that will force the degree of extension is n. And if there are any roots repeating, then it will be less than n. So this will be the degree will be less than equal to n. So now we have this finite extension. So we'll consider that we choose that n of f, that this finite extension we have considered. So this is e, this is f, this is field extension, and we do not know that if this is finite or not. So we'll consider we have considered n is a extension which is finite. So we'll choose that this n is a extension such that the degree of this extension n over f, or the what we say, that degree of this finite extension is maximum. So it's a maximal extension. Okay, then we want to prove that this n is equal to e. Okay, so since it is maximum extension, finite extension, so let's say theta belongs to E and M be the subfield of E generated by N and theta. So theta is just any element of E and M is a subfield that is generated by N and theta. So N is a finite extension and theta is any extra element. So M is subfield. We want to show that M is equal to. But we want to show that N is equal to E. But since we have considered this subfield M, M will be equal to N. Why? Because N was a M will be equal to N. Yeah, M will be automatically will equal to E. No, because of maximality, we will get that the degree of extension M over F and N over F is same. Why? Because M is N was a maximal extension, finite extension, and M is one which contains it is generated by N and extra element theta. So it will have same degree of extension. Okay. So, but now we have this M. So M is contained inside N. So M over F equal to, so M over N into N over F. But we can note that M over N is a degree 1 extension because N is maximal and M is one which has this theta, but theta is inside N. So this has degree of M over N is 1. That forces M is equal to N, and that forces theta inside N, and that's why N is equal to, so N is equal to what? E, because theta was just any element of E. So we got that N is equal to E, and N is a finite, so E over F is finite normal extension. Now it is remains to show that E over F is a normal extension. So that we want to show that E over F is normal. So already we have this is separable extension. So and it is finite. So we can write E is equal to F of alpha for some alpha. And since we know that these elements sigma 1, sigma n are distinct, and sigma 1 of alpha, the images of alpha under this automorphisms, which are the elements of G, are distinct. So we know that the extension is normal if and only if it is the splitting field of some polynomial over base field. So we'll take the polynomial. So we'll take the polynomial over F, which will be the splitting field of element alpha, which is element of E. Okay, so this is for some alpha belongs to E. So we will need to find a polynomial which is the splitting, which will generate the splitting field of the F over this element E, alpha of E. So consider g of x. So what will be that polynomial? That polynomial will be generated by these elements only. So sigma I of sigma I of alpha. This polynomial belongs to f of x, and it has degree, and since there are n among them, so it has degree n, and it is the minimal polynomial of alpha. Which is equal to, so the among this all the automorphism there will be identity automorphism, so we can say that this is for this automorphism identity. So we got that this g of x is a, so this g of x is a minimal polynomial for alpha, which is any element of E. So we want to show that this g of x will generate the splitting field. So g of x, thus g of x will generate splitting field sorry E is so this alpha is from E, so E is n, so E will be splitting field of this polynomial g of x. G was f of x. So g of x is a polynomial over f whose all the roots, this sigma is of alpha, they lie inside E, and the degree of g of x is n, so it is minimal polynomial by using that same argument for which we have given for normal separable extension. So g of x is a minimal polynomial which generates the splitting field E. So that's why, so we know that by result that the extension is normal if it is if and only if it is splitting field of some polynomial over base field. So E or F is a normal extension. Normal extension, and what will be the degree of E or F? It is normal and separable also, so it will have degree exactly n. So we have this group G whose elements were sigma 1 sigma n, and this group of course it will be contained inside the Galois group. So we have shown that this Galois group G of E over F whose degree is n. So what will be the order of G of E over F? It will be equal to n. So now G is contained inside this Galois group. So we have considered this group G, and we got that the order of so this has degree n. this is order n, and we have got this extension, and we have proved that for any extension there is a Galois group associated with it. So this is the Galois group associated with that extension, and this G also has degree order n. So order of this is same, so they have same order. So therefore G will be equal to, and they are group of automorphisms, right? Or same symbol, so there will n symbol. So therefore G is equal to G of E over F. So hence we have proved that given the group G of automorphisms which fixes field F, there is a Galois extension E over F associated with it. Thanks for watching.